We introduce Backprop-MPDM, an efficient gradient-based optimization for reliably evaluating policies while accounting for tracking and prediction uncertainty in a dynamic environment. Here, the robot is evaluating moving towards its goal GR while avoiding obstacles. The most likely outcome is benign, and there are several near misses, but there is one configuration that results in a collision, as denoted by the red lines. Policy evaluation must account for such outcomes. Another way to view this is that the cost function is very spiky because the policies themselves try to avoid collision, and small changes in the initial configurations can result in very different outcomes. Random sampling misses potentially dangerous outcomes, resulting in unreliable navigation. Risk-aware MPDM casts policy evaluation into a search for the most risky outcome. However, this optimization problem still has a large space of possible pedestrian configurations to deal with. Backprop-MPDM quickly discovers such outcomes through a gradient-based search. The key idea is to represent a forward simulation as a deep network, where each layer represents a single simulation step. Each time step is decomposed into two pieces: a set of policy-specific rules defining the forces that act upon each agent, and a set of kinematic rules that restrict their motion. We penalize bad interactions throughout the forward rollout and not just those that end in a bad interaction. Therefore, unlike most deep networks, our cost function is not just computed at the final output, but rather consists of partial costs, L, accumulated at each time step. Even then, the same backpropagation machinery can be used to compute accurate gradients efficiently. Using these gradients, a benign initial configuration is perturbed towards increasingly risky outcomes until convergence. We ran several real-world experiments for commonly occurring crossing scenarios. Backprop-MPDM can evaluate more policies reliably in real time than previously possible, which significantly reduces the stop-and-go motion. In another set of experiments, volunteers were asked to move randomly from one cone to another. Quick replanning enables the robot to navigate reliably despite the pedestrian's sudden change in direction. With the improved flexibility, we observe that Backprop-MPDM can find safe policies even with the volunteers actively trying to mess with the robot. This allows the robot to progress towards its goal safely. Thank you for your attention. I look forward to meeting with you at the poster session.